Now let's take a look back at what torque is and how torque, moment of inertia, and angular acceleration are related. So back last class, we talked about the sum of our torques, and whatever those are all added together is going to be equal to your moment of inertia times your angular acceleration. Well, now we've talked a little bit more about what moment of inertia is. Now we're going to focus on putting all these pieces together. So torque, as a reminder, is equal to your force times the distance that's perpendicular, or it is your distance times how much force is perpendicular. Now, the way that they do this, because this is kind of messy, even though I think this makes more sense, is that you could say this in a different way and say that torque is equal to force times your distance times the sine of the angle between the two. Now, when these two things are perpendicular, the angle between your force and distance is 90 degrees, and sine of 90 degrees is equal to 1. So then this part will just go away, and all you'll be left with is that torque is equal to force times distance. And almost all the time, that's exactly what we're going to be worrying about, is just that torque is equal to force times distance. So while sitting in a swivel chair, you push against the floor with your heel to make the chair spin. The 7 newtons of frictional force is applied at a point 40 centimeters from the chair's rotation axis in the direction that causes the greatest angular acceleration. If that angular acceleration is 1.8 radians per second squared, what is the total moment of inertia about the axis of you and the chair? Pause this and resume when you have an answer or you're stuck. If you're stuck, let's start here. I want you to remember first what I just said about torque. So in this case, the torque that is causing you to rotate is going to be the torque from you pushing on the floor. And so your torque caused by the push is going to be equal to your moment of inertia times your angular acceleration. If you think you're good now, pause and then resume. And torque is force times distance. So whatever that force is that I pushed with times the distance I pushed with. So now I just need to plug in the numbers. So the force I was pushing with was 7 newtons, and the distance I was pushing at was 0.40 meters from the center of my rotation of axis. So remember that it needs to be in meters. Then this is equal to my moment of inertia times my angular acceleration. That was 1.8 radians per second squared. Plug that in, and I get 1.56 kilogram meters squared for my moment of inertia. So, what would cause a bigger angular acceleration? You're going to watch a demonstration in a moment here. This is a contraption where you can move these little weights in and out. You can adjust where this string is wrapped on the center. And this little weight is going to, as it unwraps here, it's going to pull down this part, causing this contraption to unroll. This is what the center looks like, where you can see where you have 3 different places you can put your string. So what would cause a bigger angular acceleration? Pause this, think about it, and then resume. So there's a couple different ways you could do this. The first is thinking about this relationship between torque, moment of inertia, and angular acceleration. So if my torque is staying the same, if I want my angular acceleration to increase, I would need to make my moment of inertia smaller. So the same torque would be easier to make it accelerate. The second way to think about this is, how do I make the torque change? Well, if I want the torque to cause a bigger angular acceleration and my moment of inertia to stay the same, then a bigger torque is going to cause a bigger angular acceleration. And torque is equal to force times distance. So there's a couple different ways I can do this. The first I talked about was decreasing the moment of inertia, and there's 2 different ways to do that. If I want my moment of inertia smaller, I either need to make my mass smaller, or I can make my radius smaller. So I can move the balls closer to the rotational axis. That'll get my radius smaller of the thing that's spinning. Or I can decrease the mass of the system. And by the system, I mean the little things that are sticking up out of on these metal bars. Or I can increase the torque because a bigger torque will cause a bigger angular acceleration. This makes sense if you think about it in terms of force. A bigger force causes a bigger acceleration, so a bigger torque will cause a bigger angular acceleration. So I can do one of two things. In order to have a bigger torque, I can apply a bigger force, so I can hang a heavier weight, or I can apply the force farther away from the rotational axis. So if I have the string wrapped around, the farther away the string is wrapped around from the center, the bigger the torque is going to be. So on this picture up here, all I need to do is put it on a bigger axle in order for it to apply a bigger torque and therefore result in a bigger angular acceleration. So now what I would like you to do is watch this video. It's called Demonstrating Rotational Inertia or Moment of Inertia, and this gentleman is called Flipping Physics. So you're going to watch this video and then resume. And while you're watching the video, I want you to see if you notice. I want you to see if you notice which of these things did he do to show a change in the angular acceleration.